Hello everyone, my name is Yaoxin. I'm a computer science PhD student at Arizona State University. I'm glad that I have the chance to present our work at the WACV 2024 conference. The paper I will be presenting is titled FELGA, Unsupervised Fragment Embedding for Fine-Grained Cross-Modal Association. In this presentation, I will briefly introduce our paper through 5 sections: introduction, motivation, approach, experiments, and conclusion. Firstly, I would like to give you a short introduction to the background of cross-modal image text retrieval. In recent years, different types of multimedia data like text, image, audio, and video are growing rapidly. All these kinds of multimedia data are referred as multimodal data. Users can search different modality data with the help of vision and language pre-trained models. By typing the description sentence of images, the search engine will embedding them and find the nearest corresponding descriptions. Nowadays, most mainstream VLP models like CLIP are designed to bridge the gap between visual and textual data by learning powerful joint embeddings for image and text. By training on massive datasets of image and their associated text descriptions, these models enable cross-modal understanding, allowing joint embedding to related image and text in a semantic meaningful way. Just a simple example, people will type in the text description, a boat on the sea in the search engine, and the expected retrieval results will be some images that contain the boat on the sea. As many of you might know, the current mainstream VLP models are primarily designed to understand and process image and the corresponding text as a whole. This approach is quite broad and looks at both modalities, visual and textual, in a global sense. Now, here exists one significant limitation. By focusing on this global perspective, these models may overlook the semantic relationships that exist in a more detailed level, or we call them the fragment level. Let's consider a real-world scenario of the image retrieval. Image a user who wants to find image based on specific query words. These words are related just to a small segments or objects within the image, not the entire picture. For example, the keyword boat in the sentence as a query, and we want to retrieve the images that contain the boat in the image, even if the boat is not the main object in that image. This is a common application and is quite challenging. To address the specific challenge, we've defined 2 tasks called the query-driven object discovery and description assignment. The goal of the query-driven object discovery is to locate the images that contain certain visual entities. In another direction, the description assignment task will start with the visual entities, not the whole image, but specific objects. The objective is to find some description sentences that contain semantic concepts associated with these visual entities. So to address this limitation and challenge, we designed the method, the fragment embedding by local and global alignment, or FELGA in short. FELGA uses an image fragment generator. This generator's job is to develop region proposals, identify specific regions in the image that might be interest. At the same time, we have the keyword detector. The detector will identify relevant semantic concepts or keywords in the sentences. Once we have the image fragments and the text fragments, it then gets to the key part. FELGA learns the fragment embeddings through what we termed local and global level alignments. This learning process is guided by the designed pseudo-label matrix. For more details, I will introduce them in the following slides. Given the n pairs of images and text without the fine-grained annotations, we designed using the unsupervised region proposal generators to generate image region proposals as the visual entity proposals bar vn. Similarly, we use the unsupervised keyword detector to generate the keywords bar tn as the semantic concept proposals. However, after we get the image and the text fragments, we still do not know their relations. So in the next slide, I will introduce how to build up the pseudo-label matrix for them. In the supervised setting, we could access the visual entity V and the semantic concept T, also known in their associations by the association label matrix L. But in our unsupervised settings, we cannot assume no relationship between them. We provided two straightforward ways to build the fragment pseudo-label matrix for the visual entity proposal bar VI and the semantic concept proposal bar TJ. The first way is termed dense connection. If the proposals are within the same pile, we assign all of them to 1, otherwise 0. The second way is termed as sparse connection. It selects only the highest relevant visual entity proposals, which has the maximum similarity scores with the corresponding semantic concept proposal. However, these two ways have certain limitations. Dense connection relies on the strong assumption that all proposals are associated with each other, which always may not be true. While the sparse connection may have a pseudo-label matrix, capturing situations where multiple visual entities are associated with the same semantic concepts, causing the difficulty in learning fragment embeddings. To address this limitation, we propose a dynamic way to construct the pseudo-label matrix. We term it dynamic connection. Firstly, we compute the local average similarity scores of all fragments. Using this as a threshold, we divided the pairs into two groups, similar group and the dissimilar group. For similar groups, we assign the pseudo-label to 1. Other group, we assign it to 0. Besides the fragment level alignment, we also consider the global level alignment. If the image and text are from the same pile, the global pseudo-label will be 1. The main idea is to strengthen the maximum similarity within the same pile, while weaken the maximum similarity from different piles. After designing the pseudo-label matrix, we introduce how to learn the fragment embeddings. We first feed the extracted proposals into the VLP model to get the unified representations. These representations will be fed into the designed FE net. The output will be the new fragment embeddings. Then we use the output to construct the fragment level affinity matrix and the global level affinity matrix. These two level affinity matrix will guide the FE net during the training. Inspired by the lift structured loss, we employ the two following laws: local contrastive loss and global contrastive loss. The local contrastive loss functions encouraged better separation and distinction among clusters in the learned embedding space. For the global contrastive loss, it emphasizes the importance of the same image text proposal pair that have the highest similarity score. To evaluate the FELGA learned fragment embeddings, we define the following things for the requirement. The MS COCO caption dataset is the training set, while the COCO detection dataset is the testing set. This combination allows us to evaluate the performance of the proposed methods in an unsupervised fashion, where annotations of visual entities and semantic concepts are not available for training. To verify our method is not limited to specific VLP models, we also select 3 VLP models: CLIP, BLIP, and BLIP v2. And the 3 baselines were considered: the dense connection, sparse connection, and the dynamic connection we introduced before. We use DETR-EG model for region proposals and keybird for keyword proposals. For quantitative evaluation, we select the mean average precision, MAP, to evaluate the performance of the learned fragment embedding. The first table shows the result of FELGA based on the CLIP model. From that table, we can find our approach FELGA achieved the best performance. Besides that, we also do an ablation study to analyze the impacts of the designed local level alignment and the global level alignment components. Both of them are very important to the FELGA model. So for more results, please refer to the paper for more details. In summary, FELGA is a novel unsupervised method for fine-grained cross-modal embeddings based on the real-world application scenarios. We also define 2 tasks: the query-driven object discovery and the description assignment. The FELGA outperforms existing VLP models in 2 tasks, and I think it can be a new baseline to facilitate future research. Future work can explore novel approaches for generating the pseudo-labels, and can better capture the true associations. For example, different images in the same training batch may share the same semantic concepts. In this case, their local pseudo-labels could be also set to 1. That's all for this presentation. Thank you for listening.